Okay, is this working? Yes, it is working. Because there's a recording, so we have to speak into the mic. Okay, it's a pleasure to introduce our speaker today, Chris Reynolds, who is a distinguished professor of astronomy at the University of Maryland. Chris, as you'll hear in a second, is a Brit. He did his undergraduate degree in theoretical physics at Trinity College, Cambridge, and then he did a master's degree in mathematics, and then he did his PhD also at Cambridge with Andy Fabian at the Institute of Astronomy, and has been an astronomer ever since. He went to the Joint Institute for Laboratory Astrophysics in Boulder for a postdoc and did a Hubble Fellowship there. And then he went to the University of Maryland. Did I miss anything? Went to the University of Maryland as an assistant professor and rose through the ranks and was, we thought, happy, but then he became the Plumian professor back at Cambridge in 2016, I think, and that's where he was until fairly recently when he bounced back across the pond to go back to the University of Maryland, where he is now he just finished his Phase A proposal for a very important potential NASA mission in this new class called Probe, which is a $1 billion mission. Chris is the principal investigator. And I think at the very end you'll mention something about that. But Chris is one of these omnivores. He's sort of trained as a theorist but does experiments, trained in astrophysics but knows all the physics. And I think today we're going to hear about some of that crosstalk. So
okay.
Take it away.
Thanks. Good. Okay, well, firstly, can you hear me? Yeah. Thanks for the invitation to come and speak to you. It's a great pleasure to be here. I was just saying to Meg, I looked up in my my list of when I was last here, and it was 21 years ago, which is terrifying. Time flies. So today I want to talk to you about what is actually really a sort of a sideline in my research. It's sometimes if you try to do real physics in an astronomy department, they poke fun at you. So for me, this is largely a sideline, but as I hope I can convince you, we can actually do some very interesting things in particle physics and looking at particle physics beyond the standard model with astrophysical observations, and that's what I'm going to be trying to convince you today. And I want to just quickly thank some of my main collaborators in this, especially the first person listed there, Julia Cis-Rains, who was my student in Cambridge, who was doing some of the work I'll be describing. And I want to also thank my funding source back when I was in Cambridge, the ERC, and of course now NASA and JSI up in Maryland. So these are the take-home messages. Just want to sort of put right up front what I'm hoping you'll take away. So there's currently a huge surge of interest in the physics community on axions and axion-like particles. So these hypothetical particles that in many can do an awful lot for physics. They are a window, if we discover them, they are a window on physics beyond the standard model of particle physics. They are very plausible dark matter candidates. They're even plausible dark energy candidates if they're in the right mass range. So in many ways, if we discover axions and we sort of open up that sector of physics, this can go a long way towards explaining many of the most profound mysteries in physics. What I'm going to be telling you today is about how we can use X-ray astronomy, so astrophysical observations with X-ray telescopes, to make some very compelling constraints, and very, very stringent constraints on this area of physics. I'm going to talk about two particular areas. One is observing accreting black holes in galaxy clusters, and another one is constraints on black hole spin, and how those observations can set some very powerful constraints on Axion-Sector physics, and potentially be a path for actually detecting this physics in the future as observations get better. And I'll also, I put this up with some hesitation because I am certainly not a string theorist, and my knowledge will fall apart if you ask me many questions about string theory. But this is a point of connection. People who are string theorists have been writing papers making predictions about the axions and axion-like particles that come out of string theory. And the constraints we have from these astrophysical observations are already starting to get into the part of parameter space where the string theorists say we might be finding things. So that's an important point of contact here with string theory. Okay, so that's the take-home messages. Let's get into it. So let me, by way of introduction, talk a little bit about the standard model and what goes beyond the standard model. And here, I know there are real particle physicists in the audience. I apologize to you ahead of time for this. I'm an astrophysicist presenting this. So the standard model of particle physics, of course, is one of the great intellectual achievements of the 20th century. It's the quantum field theory that describes electromagnetism, the weak force, the strong force, and it successfully describes all the experimental data that we have on those forces and the interactions of them. So it really, and the pinnacle of that was the discovery of the Higgs boson in 2012. In 2012, the Higgs boson was discovered at the LHC, and that really sort of cemented this whole a tremendous model together. However, even though it explains all the observational data, we know it cannot be complete. We know it's not complete for various reasons. Firstly, it doesn't describe gravity. So modern physics is this Frankenstein construction of the standard model of particle physics doing everything apart from gravity, and then general relativity doing gravity. But famously, those two frameworks don't play well together. Secondly, the standard model, there is no natural explanation or even unnatural explanation in it for dark matter, which we know is the dominant form of matter in the universe. And there's no explanation for dark energy, the phenomena that's causing the universe, the acceleration of the universe, the expansion of the universe. And then finally, even the standard model alone as a theory, it works, but it's got free parameters to it, and there's a lot of fine-tuning that's needed in the standard model, and there's unnatural aspects to the standard model. So, there's, of course, within the physics community, a great impetus to go beyond the standard model and have experiments that can probe that regime. So I'm going to pull one thread here on one of these on the fine-tuning problems. And this is sort of historically the route into this field of axions. One of the fine-tuning problems in the standard model of particle physics is known as the strong CP problem. So what is a strong CP problem? C is the operation of charge conjugation. So imagine you take a system, you take all the particles in it, and you transform them into antiparticles. You flip their charges and flip all the other quantum numbers. P is a parity transformation in the system. So you take your physical system and you do the mirror image of it. And CP is the combination of those two things. So we take a physical system, we turn every particle into antiparticle, and we reflect it. Now, there's no mathematical reason within the standard model, when you write down the Lagrangian of the standard model, there's no mathematical reason why when you do that operation, the CP operation, the physics should remain the same. There should be interactions for which, when you do the parity flip, the physics changes. And in fact, with the weak force, you find that the weak force is not symmetric to that transformation. So there are weak interactions that violate CP symmetry. This is one of the reasons why there's an asymmetry between matter and antimatter. With the strong force, however, the experimental data put very, very, very tight limits on the violation of CP. So, if you take a system that's interacting with a strong force and you do this transformation of it, experimentally the physics stays the same. But within the standard model, there is no mathematical reason why that must be true. So this is a very serious problem in the standard model straight up. So back in the 70s, this was recognized, and Pecci and Quinn famously came up with a fix to this. So this is now going beyond the standard model, but it's considered this is now a map for how a lot of this kind of physics goes. So they introduced a new symmetry into the theory, so a new internal symmetry in the theory, a U1 symmetry, and this introduces a new field, and essentially the term that violates CP symmetry in the strong force has a coefficient in front of it, and in the standard model, you basically just have to say that coefficient is extremely small. What this does is it turns that coefficient into a dynamical field, which naturally decays to something that's very small. Okay, so it turns that coefficient into something which is now dynamical and naturally decays through symmetry breaking to something that's very small. So it was shown by, so that was Pitchy and Quinn, and very quickly after that, Wilczek and Weinberg predicted that there would be a new particle that would come out of this symmetry, a spin zero, uncharged boson, and they called this the Axion. So the name Axion comes from a washing detergent, and because it cleans QCD of the CP, the strong CP problem. Okay, so Axion is literally is a washing detergent, but that's what I guess his name. So of course, with the beauty of gauge theory, you come up, you put a new symmetry in, you turn the gauge theory handle, you can start to predict what kind of interactions this new field, this new particle would undergo with standard model particles. And so, for example, you find that axions will interact with photons in a very particular way. And we just, here's a Feynman diagram. For example, you've got a photon traveling along. It can interact with another photon, which could be a virtual photon from, say, a magnetic field, and it will convert into an axion, or vice versa. An axion can convert into a photon with an interaction through another virtual photon. So that's an important process we'll talk about later. That's called the Primakov process. So that's the standard, the standard, what's called QCD axion. Now, going beyond that, if we now go to general beyond standard model theories, again, there's been a huge, vast space of theories extending the standard model. One of the most discussed ones are string theory. It turns out these kind of particles, or these extra symmetries in the theory which lead to these extra particles, is a very, very generic outcome of beyond standard model physics. So for one way to see that, intuitively, in string theory, for example, is in string theory, the fundamental theory has to be put in a large number of dimensions, typically 11 dimensions, and then to get back to the 4 dimensions, the 3 plus 1 dimensions of our universe, you have to compactify lots of dimensions. You have to fold them up, and there's a very large number of ways of folding up these space-times so that you can get back down to 4 dimensions, and so you have these extremely complicated folded structures, these manifolds, so-called Clausius manifolds. And once you start to fold up these space-times in so many different ways, there's a huge number of possible topologies that can result. And the number of little space-time loops where you can sort of be going around structures that have been folded up, there's a very, very large number of ways of doing that. And some of those can play the role of that extra symmetry that looked like a Petrie-Quinn symmetry. So when you take these space-times and you fold them, you compactify them like this, there's a very large number of these kind of extra particles that can then come out of these theories. So this gives rise to, these are not quite the same as the original axions that Petrie and Quinn wrote down. So these are called axion-like particles, and they can have you can have many such particles coming from a given theory. So you can have large families of these particles. They can have a large range of masses, and there can be a large range in their coupling constants to the other the other fields. So just to show you one calculation of from some toy string theories from a paper by Magenda et al. In 23. On the x-axis here, we have the mass of potential particles. See the scale? Extreme. I mean, 10 to the minus 100 is, mathematicians know that is not zero. So these are not massless particles, but it's pretty damn close to massless. And all the way up to very, very, so essentially logarithmically extremely large range of masses. On the y-axis here is the coupling constant. It's the strength of coupling, in this case, between photons, between the electromagnetic field and the axions. And you can see, I won't go through this, but basically the little diamond shapes here are the most realistic of the string theories that they've calculated here. They're the ones with the most complicated compactifications. And you can start to see, start to remember this number. The coupling constants they start to predict are, up around about a few 10 to the minus 13, around about 10 to the minus 13, with a huge range of masses that go through. Okay, so we sort of just, getting towards the end of this introduction. Say, well, what good are these kind of things? Well, you have a huge range of masses here. Anything that's less than 10 to the minus 30, the Compton wavelength of that particle is larger than our cosmic horizon. Okay? The particle doesn't fit in our observable universe. And in that case, as the universe is expanding, it actually will act as a dark energy. It'll actually be a fixed energy density as the field is expanding. So particles which are, if there's a lot of energy density in particles that are that low mass, that's your dark energy. Okay. Particles above 10 to the minus 30 in mass, if they're generated in the early universe through non-thermal processes, we're talking about physics that's occurring around about inflation or maybe just after inflation, you can have non-thermal processes that create very cold, very low energy, but very low mass particles. That can act essentially as a cold dark matter. One particularly fun thing, particles which are right around about 10 to the minus 22, 10 to the minus 23, have Compton wavelengths of about galaxy size. And so if you do a structure formation calculation using those, this is a structure formation calculation using such a dark matter. This is known as fuzzy dark matter. As the dark matter, these are galaxies that are forming, and as the dark matter filaments between the galaxies are collapsing, you can actually get quantum interference patterns. It's occurring, and you can have condensates of these because these are bosons. You have condensates of these axions forming. So the structure formation process can actually be rich in a way that goes beyond the usual cold dark matter physics. So now, of course, if the axion is significantly more massive than 10 to the minus 22, the Compton wavelength is then much smaller, and it can act pretty much as a cold dark matter. It would be indistinguishable from cold dark matter. This made its way onto the XKCD map of dark matter candidates. Axions are down here, along with other fun particles and objects. So right, how to hunt for axions. So like anything in this game, as a spoiler alert, we haven't found them yet, but we have to define a hunting ground that we're gonna go to and try and systematically rule out as much as we can. So the hunting ground, this is coming back to that same plot I showed you for the string theory, is axion mass, and this is the only plot where it will be in indecipherable units. Axion mass versus the axion photon coupling constant. And that's not the only possible choice. The physics here is very rich. So you can think about axion photon coupling, you can think about axion nucleon coupling, axion electron coupling. There are whole communities that look at each one of these things, but I'm going to be focusing on axion photon coupling. So just to sort of give you a quick lay of the land, boom. This is sort of a summary plot of work by. At lunch we were trying to decide whether it was dozens of groups or hundreds of groups in this space. You can see that there's each one of these blocks is a separate experiment that has done this. So there's an entire semester's worth of colloquia in here that you could have. You get fed up of it eventually. But let me just, on this plot, before we move on, highlight some fundamental differences between some of the experiments that are done here. These blue regions are experiments; they're all laboratory experiments, which are trying to identify the axions that are in the dark matter that are in this room right now. Okay, so we live in a galactic halo that's got dark matter. If that dark matter is axionic matter, then you can build an experiment that tries to couple into that. For example, you can set up a magnetic resonator that tries to couple into those axions, and you can constrain that. So that's what the blue regions are. And there's a lot of work done here on that kind of thing. So some of these things that dig extremely deeply into the parameter space are resonant cavity systems, where you have very tightly, finely tuned resonant cavity with a magnetic field, and if there's an axion at just the right mass, it can couple into that field and oscillate it, and you can detect it. The red region is a set of experiments called light shining through wall experiments. I'll talk about in a second. The green region, these are all various astrophysical probes, not of dark matter, but just of the very existence of axions. If axions exist, then they affect astrophysics in various ways. They don't have to be dark matter. It could be dark matter something else yet again. But if axions exist, they will affect astrophysics, and we can look for that signature. So that's what the green is. And you can see that little line there saying Chandra, which is this bottom line here, that actually is one of the deepest bites into this part of the parameter space. That's what I'm going to be talking about for a chunk of this colloquium. Okay, so let's take a step back, and before describing exactly what we've done, just walk you through step by step a little bit of the physics here. So imagine you have a beam of photons. Just a laser beam, say, that's propagating along. And then you have a magnetic field that's present. And in particular, I mean, my artistic abilities couldn't quite demonstrate this, but in particular, this magnetic field should have a component that, or rather the polarization of the photon beam should have a component that projects onto the magnetic field. Okay. Now, in the standard model, and this is not a crazy magnetic field. This is not a supercritical magnetic field or anything like that. This is just a regular old, a boring magnetic field. Standard model says nothing interesting happens here. The photon beam can quite happily travel through the magnetic field. If axions are present, however, if axions exist, if they're just in the theory, that is not true anymore. What happens then is that the propagating state here is not a pure photon beam state. If you sort of go into the theory here, if axions are present, there's terms in the Lagrangian, in the standard model Lagrangian, that look like this. This is just the standard electromagnetism, but in particular, you then get the axion term, and you get a coupling here between the axion and the electromagnetic field. And when you write that down and solve for the propagation, you find the propagating state is not a pure photon beam. And it's not a pure axion beam. It's a mix of the two. So the propagating eigenstate is actually a superposition of photons and axions. For those of you who are familiar with neutrino oscillations, it's exactly the same mathematics as that. For a propagating neutrino beam, the eigenstate is not all electron neutrinos or muon neutrinos. It's a mix, so you have oscillation between the states. So it affects the basic propagation of photons. So this is the basis for the light shining through wall experiments, which I briefly mentioned earlier. So the idea here is you have a laser, you shine the laser through a cavity that has magnetic fields. You hope that some of the photons will be turning into axions. They'll go through a wall. Of course, photons don't go through a wall, but the axions will. And on the other side, in a presumably dark room, you have another cavity with a magnetic field. You're trying to convert those axions back into photons, and you try and detect them. Okay, so that big red swathe of experiments at the top were generated from the non-detection of those kind of experiments. Another thing you can do, of course, is to find naturally a powerful source of axions, and one compelling one is the sun. So if axions exist, the core of the sun should be a prominent axion source. That this is calculations for a particular assumed coupling constant of what the flux of axions from the core of the sun would be. The physics here, or one of the production mechanisms, are photons in the sun interacting in the Coulomb fields of the particle of the protons in the sun. The Coulomb fields are providing that virtual photon that converts into axions. So there's an axion production in the sun. And then what you do is you take an X-ray telescope, you lock it in a light-proof box, which as an X-ray astronomer is. You lock your X-ray telescope in a light-proof box with a strong magnetic field, and you point it at the sun, and you're trying to convert the axions from the sun back into X-rays and detect them. Okay. And one of the most successful of those experiments is CAST, which is in CERN. It's the CERN Axion Solar Telescope. You can see that it's situated horizontally, so you look at the sun at sunrise, and you look at the sun at sunset, and you try to find the axions there. So, of course, the non-detection of those led to, I didn't have that on there, is that big region there, CAST. That's non-detection of non-detection. Okay, so let's now pivot to astrophysics and how astrophysics. So, of course, the thing about the universe is the universe can provide extremes that we can't generate in the laboratory. And in particular, if you look at something like CAST, the sensitivity of this is proportional to G, that's the coupling constant. So sensitivity meaning like the probability of converting your axions back into photons depends upon the coupling constant, and then the magnetic field strength, and then the path length you have, all squared. So magnetic field length times path length is an important quantity there.
Why X-rays? Why can't I do this with optical filter?
For the sun, it's because the core of the sun is 15 million Kelvin. That's 1.5 keV. So the energy of the axions coming out of the solar core is naturally about 1.5 keV. So they'll turn into few keV photons.
Yet on the Axion, you had a whole range covering all the way down to pico electron volts.
Oh yeah. So there's two separate things. One is the mass of the axion, and then one is the energy of the axion. So in this case, the axions can be very light, but they'll be ultra-relativistic. They're ultra-relativistic in this case.
These are expected to be very light from the sun.
Yeah. The more massive ones don't make it out. Okay, so astrophysics, we have extremes, and one of the particular extremes I'm going to pursue is we have extreme lengths that we can apply. So let's go to galaxy clusters, and you can survey all the astrophysical systems out there and see where would this effect be maximized, and again there could be a whole colloquia on whether you can do this around neutron stars or whether you can do this around white dwarfs. But it turns out that clusters are a very, very compelling object. So galaxy clusters, for those who who don't think all the time about galaxy clusters, especially for the physicists here, they are very poorly named objects. Okay, so galaxy clusters, of course, are, you can look at this, you see a bunch of galaxies. They're all orbiting in the neutral gravitational field. But of course, the actual galaxies you see are kind of a tracer here. That's not really what's going on. The dominant source, the dominant mass is a big dark matter halo. So the dominant mass, dominant gravity is a dark matter halo. But even the baryonic matter is not dominated by the galaxies. The baryonic matter is dominated by a hot magnetized plasma that fills the space between the galaxies. So in fact, this purple haze here is actually an X-ray image of that hot gas. It's called the intracluster medium, and the typical parameters of it are up here. It's very tenuous, just less than a particle per cc. It's hot, so 1 to 10 keV, that's 10 to the 7 to 10 to the 8 Kelvin. The typical length scales of this are the whole cluster, so typical length scales of order hundreds of kiloparsecs, so million light years, and it's magnetized. It's not strong by many people's measures, but it's of the order of 1 to 10 microgauss. Now, how do we know it's magnetized? I can answer questions like this if you're more interested, but in brief, we know it's magnetized because if we look at polarized radio sources that are either in the cluster or behind the cluster, we see the characteristic rotation of the polarization from Faraday rotation as that polarized signal is propagating through the cluster. And we can track that in detail, we can look at its wavelength dependence, and we can measure the integral of the line of sight of the density times magnetic field. So we can back out from that modulo reversals, which we have to worry about statistically. We can back out of that what the magnetic field strength is in these clusters. Okay, so that's the cluster. So let's do an interesting calculation here. Let's take just a block of plasma that looks something like this. This say a magnetic field strength of 10 microgauss, a path length of say 100 kiloparsecs, and let's do a calculation of a photon beam propagating through it with axion physics and see what happens to it. And there's many people who have done such calculations, but I want to highlight a code that James Matthews, who is my postdoc in Cambridge and now is in Oxford, put together. He wrote a code called ALPRO, Axion-like particle propagation, which is on GitHub. You can use it if you wish. And this is that calculation. So this is photon energy here, and this is the probability that the photon survives passage through that system. And these are the assumed axion parameters just for this particular calculation. And you can see what happens to very low energy photons actually are not converted. And then as you start to hit a particular energy, you get this oscillation that occurs where you're looking at, it's oscillating between photons and axions as going through this block. What you care about is what exits the system. So as you tune through different energies, you tune through different wavelengths of the oscillation, you'll oscillate the signal that comes out the other end, and then for highest energies, it trails off it.
You presume that the entire ecosystem is magnetized at this level.
So this was an experiment. I'll show you what we actually do in a second. Yeah. But that's a really important question. Yeah. Briefly, I won't labor on this at all, but there's actually a very nice connection. You can do a first order perturbation theory of this conversion of photons into axions, and show that there's a beautiful connection between the shape of these survival curves and the Fourier transform of the structure of the magnetic field along the line of sight. You can actually make that connection formal. And so in this very simple case of just a uniform blob, a uniform box, you can solve the problem in pencil and paper, and this is the conversion probability that you get. So you can see that has this sort of sign property to it. Okay, now, as Priya says, real clusters are not uniform boxes. They are highly turbulent systems. So this is just a nice numerical calculation of what the magnetic field in the cluster looks like. It's typically a very turbulent system. Again, a ton of interesting fluid dynamics that goes on here. But really what you're looking at is the propagation through this kind of system. And if you do that kind of calculation, what you find is it looks something more like this. So you get rid of that very nice, simple oscillation. You replace it with something that's messier, but it has the same basic character to it. Same character in the sense that this typical transition point is at the same area, and the low energies, the oscillation is very fast. As you go to high energies, the typical delta E becomes much higher. Now, one thing I wanted to highlight here, but both in these simple calculations here and then in this, was this grey band. This grey band is what I refer to as the classical X-ray astronomy band, 1 to 10 keV, where we build all our X-ray telescopes in that band. And so this is why clusters of galaxies and X-ray astronomy and axions all line up, because the typical parameters that the clusters give us mean that this interesting physics is happening in the X-ray band where we can look. So here's the experiment we do. We find a nice source of light, of X-rays in the center of a cluster, and the classic one is an accreting black hole. So we find an AGN, an active galactic nucleus, in the core of a cluster, and then we characterize. We do our best to characterize the propagation of that out to our X-ray telescope. In particular, what we're looking at are spectral distortions. If the AGN has a very nice, well-characterized, quotes, boring spectrum, then we can set limits on the degree to which the axion physics has imprinted fluctuations on that spectrum. And we can turn the limits on those fluctuations into limits on the axions. So that's what we're doing. And these here are just some calculations of realistic photon survival curves through this kind of system. I want to just highlight the run of papers that have pioneered this technique, starting with Walter and Brun in 2013. So I'll show you sort of two particular targets where we did this. Here's one. Those of you who know me know that this is one of my favorite clusters. This is the Perseus cluster of galaxies, a remarkable object for many astrophysical reasons. This is the optical image. If you look at it with Chandra, the Chandra X-ray telescope, you see this. So this is the hot intercluster medium, about 4 keV temperature. The structure in here is the central AGN, central black hole, injecting energy into the core of this cluster and heating it up and exercising feedback on the system. So there's a ton of really neat astrophysics that's going on here. But this projector doesn't quite see it, but the very center here, there's a little black dot in the very center of that. I don't know if you can see it. You can see it on this screen, but not up there. There is not a little black dot at the center of Perseus. The little black dot that's there is because that central pixel is completely blown out. It's saturated. Okay. And if you take Chandra and you drop the diffraction grating into the beam, you get this. Okay. So this is the cluster emission here. And this is the dispersed spectrum of the extremely bright AGN that sits at the center of Perseus. So what we did was we used Chandra to get the best ever spectrum of this object, and this is the spectrum. So it's a nice, boring power law spectrum that sails all the way from 1 keV through to almost 10 keV. With the deviations from just a boring power law being at the level of just 2 or 3%. This is not why I did this observation. I did this observation because I wanted to discover all the interesting things in this spectrum and do astrophysics with it. But that's what you got. So, but this is a beautiful spectrum to do the Axion experiment with. So, the first thing you need to do is to make some libraries. Well, okay, you're looking at the signal propagating through this cluster. The immediate problem, which you probably already thought of, is as I'm trying to model the Axion signal, I don't know what the structure of the field in the cluster is. I mean, I know statistically how strong the field is, but it's in a turbulent state, and the details of where those fluctuations dip and peak depends upon the details of that. So I'm not going to be able to do a straight up fitting here. So the exercise we do is for given sets of Axion parameters, so for given Axion masses and given Axion coupling constants, we come up with a very large number of realizations of what that field structure looks like along the line of sight. And we build up large libraries of what these fluctuation curves look like. And then what we do is we just take our AGN model, which is a power law, we apply the Axion physics of a particular model to it, we compare it to the data, and through this way, we just throw the entire library of Axion curves at it. So what we're trying to do is just in a statistical way to say, for a given Axion parameter, with the typical fluctuations, disagree with the data. And through this exercise, we can do that. So these are the exclusion curves we got for that object. We can exclude everything above a little less than 10 to the minus 12. Now remember, so I want you to remind you of that trigger point for interesting string theory, 10 to the minus 13. Okay, it's only just down there, and we can go down to here. Now you can see that the constraints start to become poor above about 10 to the minus 12 EV there. Why is that? Because the signal is propagating through a cluster, and the cluster there's a characteristic plasma frequency in that cluster. And for axions that are more massive than the characteristic mass associated with that plasma frequency, the conversion is strongly suppressed. One way of thinking about it is as you've got a photon propagating along that's hopping into a particle state, hopping into an axion state, and then going back to a photon. How does it do that and preserve, both conserve energy and momentum? Well, the only way it can do that by conserving energy and momentum is if it's sharing momentum with plasma modes. And if the particle is too massive, it just can't do that. It can't share the momentum with the plasma modes. Okay, so for sufficiently massive axions, the constraints start to fall apart.
Wait,
Yeah.
was that raw data, or was that corrected for photoelectric absorption of the elements in the cluster medium?
Excellent question. That is corrected. So what we do is I showed a very simple bare model here, but we can put as much complexity as we want into the AGN model. And so I actually did put photoelectric absorption in here. And in fact, in the curve I just showed you, we put a partial covering photoelectric absorption in. There's evidence that the X-ray source in Perseus is actually structured, and each part of it has different absorption. So we put that complexity in there too. Yeah.
Another question. So am I correct in assuming that the strength of the signal basically correlates with the integral of the magnetic field along the line of sight?
Yes.
So what fraction of that comes from the source itself, right? This is a very small part.
Oh, good question.
There's a huge magnetic field.
So good question. So yes, and with a caveat, which is the remember what I was saying about the plasma frequency. The very center of the cluster is so dense that the conversion probability is suppressed. So the actual, when you look at Perseus, for example, and you look at where the conversion is going to happen, it's from like 10 kiloparsecs or so outwards, which nicely, quotes nicely, excludes that horribly complicated region in the center. But you're right, this is an integral constraint. Okay, so there's a model of the cluster field that has to go in there.
So the magnetic field right around the black hole is not a problem.
Okay, so very quickly after that, with my student Julia, we found a better object to do this. There's a remark again for the astrophysicists. There's a remarkable quasar called H1821, redshift of 0.3. It's incredibly powerful. It's one of the most luminous objects in the local universe, and it sits in the middle of a cool core cluster of galaxies. And so with that, again, we looked at archival Chandra data. We didn't actually have to get new data. We've got a beautiful power law with some complexity in it. I mean, you know, my day job is looking at complexity in AGN spectra, so we modeled that. And we came up with what is still today the strongest constraint on axions in that low mass range, which is you know, this is the 99.7% confidence region. So if we look at the Axion constraint plot, and I just putting this up, I want to highlight there's this wonderful website that's run by Kieran O'Hare, who I believe is in Australia, who compiles it's always kept up to date. He compiles the latest limits on axions from every direction, and comes up with these wonderful graphics for it. So huge shout out to him. But so this constraint here, which is now biting down here, and of course runs all the way off into very low masses, is the constraint from Julia. So how am I doing for time? So that's the leading constraint right now in axions in this mass. Now, looping briefly back to string theory, particularly show this plot. So this is the same paper I showed that huge range of masses from. If you start to look at where do you really expect to start uncovering these kind of particles in that picture, that's in the coupling constant space. That's this purple region there, and that line is where we currently are. Okay, so we are really on the cusp of, if we can start to dig down with future studies of this, you might start to get some surprises. And I'll come at the very end to how we might be able to dig down further. Okay. I want to spend just a few minutes talking about another really neat technique, a rather different technique, but again one based on X-ray astronomy that we can use for constraining this physics, and that's the idea of using what's called black hole superradiance. So the physics here is really quite beautiful. You can consider a black hole. You've got a black hole of a particular mass, and it's spinning. It's a black hole with a particular spin to it. And if an axion-like particle exists, and it's got a mass such that the Compton wavelength of that particle is something like about 10 gravitational radii of the black hole, then it matches very nicely. And in principle, the axion-like particles can now form orbitals around that black hole. Now, that would be uninteresting if there wasn't a reason why they would do that, but the interesting reason is that if the black hole is rapidly spinning, it turns out there's an instability which can take spin energy and dump it into the boson field and grow that boson field exponentially around the black hole. So again, there's been a slew of papers on this starting 15 plus years ago. And my involvement was on this most recent paper by Sebastian Huff. So in doing this, you're sucking spin energy out of the black hole. Therefore, you're spinning the black hole down. So as an astrophysicist, if I can go out and find a black hole that's spinning extremely quickly, I can rule this out, as long as the black hole's lived long enough to go through this. Just to sort of briefly share, these are some calculations by Sebastian of the superradiance growth rate. This is the growth rate of that cloud in units of the mass of the black hole. So you can see that, for example, up at this is 10 to the minus 8 m, so 10 to the minus 8 light crossing times the black hole. That's extremely fast growth rate for a cloud around the black hole. And just in brief, if you want to know the physics of this, it's quite straightforward in principle. The axions are governed in this case by a very simple bosonic wave equation. And if you take this wave equation and you solve it in the Kerr space-time, which is described in the spinning black hole, then in the Kerr space-time, there are negative energy modes of this, sort of a counterpart to negative energy orbits around in the Kerr black hole. And that can lead to an instability. That can lead to an instability of taking the spin energy and dumping it into some of these modes. And these modes, they form the analogy of orbitals. It's like an atom. So these are called gravitational atoms. And the calculations show that what tends to happen is you dump the energy into this mode. This is n equals 1, n equals 2, l equals 1, m equals 1. So equivalent of a 2p mode, I think, in a hydrogen atom. And then that can share energy with these higher order modes. And eventually, if the energy gets shared enough to these higher order modes, they decay away, and it radiates the energy and gravitational waves. So, if we can set limits on black hole spin, we can set limits on this process happening. And guess what? With X-ray astronomy, for a long time now, we've been trying to play the game of setting limits on black hole spin. And just a very quick, I sometimes do give whole colloquia on this particular subject, but one powerful technique for doing that is so-called X-ray reflection. So AGN are powerful X-ray sources, and here we have a black hole with an accretion disk surrounding it and a sort of generically placed X-ray source here. The X-ray source is irradiating the disk, and the disk is typically, in many of the systems we look at, relatively cold. So it's not fully ionized plasma. It's a plasma that's still got some combined atoms in it. And so when the X-rays irradiate the surface layers of this disk, it excites emission lines. It excites fluorescent lines, for example. And one of the most important ones we see, this is a calculation of a spectrum that we would get off the disk. One of the most important ones is a line from iron, which is a little above 6 keV. This is all happening around in the very close by regions around a black hole. So you have Doppler shifts from the relativistic motion, or mildly relativistic motion in the black hole, and you've got strong gravitational redshifts that are affecting the line profile. So what happens is you have a line, your lines are not narrow lines, they are skewed into lines that have this kind of profile by the combined action of Doppler shifts and gravitational redshifts. And this gives you a probe of the black hole spin, because, what I'm about to say is not an uncontroversial statement, but if the accretion disk cares about the innermost stable circular orbit around a black hole, the point where material stops going in circles and falls in, if the accretion disk cares about that location, if that sets the effective inner edge of where you get these signatures, then as the black hole is spinning more rapidly, the innermost stable circular orbit is moving inwards. And so these relativistic effects become more pronounced for more rapidly spinning black holes. So that's what you're seeing here. The blue profile is for a rapidly spinning black hole. The black profile is a zero spin, and then the red is for a retrograde spin. So we've been at this for many years of trying to look at these features in data. This is one particular object that Don Walton, who's now at University of Hertfordshire, has been looking at. This is IRAS 09149. And you analyze the data, and once you take out absorption that exists, here is that broad iron line. Here's what's called the Compton reflection hump, which is the other part of this feature that's reflected to this. So you can model these data and get black hole spin. So for this object, you model the data in a multi-parameter sense because there's a lot of degenerate parameters here. But when you do that, you get a black hole spin of 0.94 with some error bars. Yes. So this is a rapidly spinning black hole. And this is just one example, but if you can compile together what we have in the literature for objects, and for supermassive black holes, this is a compilation that I did and Julia did a couple of years ago, and you see there's a large number of black holes that are rapidly spinning here. So we can turn this into a limit on the presence of axion-like particles. So if you're interested, there's Sebastian who did a nice job here, and the name of the game is you take your spin data. So here we have spin and mass. So you have to have some idea of what the black hole mass is as well as what the black hole spin is. And with this particular object, this is the same object I just showed the plot for, the IRS-09 object. There is data from the VLT gravity experiment, which actually is a optical, near-infrared rather, interferometer that can actually resolve in beautiful detail the rotating broad line region of this object. So we have a good idea of what the mass is in this object. So now what we can do is say, well, okay, what does this imply for a constraint on axion-like particles? And we can put these exclusion curves on here for a given black hole, for a given axion mass and a given assumed coupling strength. We can say, well, we can just about agree with this data here. We can sort of clip the edge of this parameter space. Now, the interesting thing about this technique is that unlike the other technique, if axions are not interacting with anything, this physics is maximized. The stronger axions interact with either standard model particles or with themselves, the more they will scatter and the more this instability will be suppressed. So you get exclusion curves that look like this. They're turned upside down from what we had before. Okay. We can say that within this mass range, this is for a stellar mass black hole, this is for a supermassive black hole, within this mass range where this tuning of the Compton wavelength to the gravitational radius is satisfied, we can rule out axion-like particles that have coupling constants of this or less, all the way down to 10 to the minus 19. 10 to the minus 19 is 1 over the Planck energy. Okay, so that's where the picture would fall apart if it was down there. So you start to put this together with what we had before, we can start to squeeze the parameter space in the future. Okay, so in the last couple of minutes, just what's next with this? In both areas, both in looking at galaxy clusters and looking at black hole spin, we need the next leap in sensitivity and performance for our X-ray telescopes. So over in Europe, one of the big endeavors is Athena, now technically new Athena. I'm just waiting for them to drop the new and come back to Athena. This is a flagship level mission from the European Space Agency, projected for launch in 2037. These things take a long time. This will be a big step in X-ray astronomy, in every respect of X-ray astronomy, across the full board, but for the physics that we're talking about as well. Athena, if you want really nice, sharp images, this is not your mission. Okay, it's got about 10 arcsecond point spread function, but it is going to have a fabulous spectrometer on it. If you're impatient for that, or you want nice, sharp images, then, as Meg says, my life for the last couple of years has been sucked up with, in a nice way, with AXIS, the Advanced X-ray Imaging Satellite. This is the front cover of the proposal we just submitted last week. And there's 750 pages that sit underneath that. This is slated for launch in the early 2030s. And again, will be a big leap in sensitivity, about 10 times the collecting area of Chandra. but will also maintain high spatial resolution, unlike Athena. So for particular physics we're talking about now, some of the things we look forward to is we'll have deep surveys. Think Hubble Deep Field, for example, and Chandra Deep Field. We'll do our deep fields. We expect to uncover something like 20,000 new AGN in those fields, and some of them will have enough photons that we can actually pull out black hole spins from up to redshift of 2, possibly, maybe even beyond 2. So we'll have information on black hole spin as a function of cosmic time. So we can start to look at these axion, these superradiance problems in that context. For the galaxy clusters, Axis will be able to take significant. So this plot here shows the Chandra observation of Perseus cluster binned up, so that we have enough photons in each of those bins to do really nice spectra with. And you see it starts to look a bit blocky once you do that. With Axis, we'll be able to get significantly better data here. And the prospect there is to be able to do these axion fluctuation problems, not just at the central AGN, but look at axion fluctuations across the whole cluster, which will dramatically expand the number of photons at play and can hopefully expand the sensitivity. Okay, so let me come back to my take-home messages, and hopefully I'll convince you that there is a lot of excitement in this field of looking for axions, and X-ray astronomy has astronomy in general. I mean, has a lot to bring to this problem, and I think the future of this is very exciting. So thank you very much.
We had a bunch of questions we're going to talk about. We can take one or two more now, I think.
Great talk, Chris. Thank you. The constraints that you showed for superradiance, you showed constraints on both the coupling strength and the mass. Was it assuming that actions of that mass are making up all the dark matter? Or there should be another constraint, right, about the density, the total energy density in those actions?
Yeah, so
Wait, I guess since the recording,
sure. Yeah. So the question was, for these constraints that come from superradiance, is there an assumption related to the dark matter, or what is the assumption related to dark? I think that's a.
Well, the question is, I would have envisioned there's another parameter, namely what is the total energy density in actions of that mass? You call it on the x-axis.
Yeah. So the axions are generated from the superradiance process. The axion cloud sucks the energy out of the black hole spin, and what sits underneath here, the part that I didn't talk about at all, is that there is then physics that will lead to an equilibrium. So there's an equilibrium state where energy is being extracted out of the black hole spin. There's interactions between those orbitals that sort of share the energy out to an outer orbital, which is then decay and dissipates. So there's an equilibrium process, and you can calculate that through for a given assumed decay constant. So yeah, I skipped the it's created, and I skipped the physics of what the equilibrium physics is, but yeah, that's.
And a very related question. So, in the process of reaching equilibrium, it would matter, right? If you are 10 to the minus 22 dark matter. See, all the dark matter problems, that's it's a slightly different mass range.
That's right. So again, this particular technique is firmly in the camp that doesn't care about dark matter. So dark matter could or could not be axions. It could be axions of a completely different mass. This is just asking the question: if those axions exist at all? If they exist, they will be created by this process.
Okay, but there's no question of them having to then equilibrate with the other axion configuration as well. In the galaxy cluster case, I was curious, your constraints actually extend this up all the way down. How far down? Where in things where?
they go all the way down to massless. Like, so if you where is it? I don't have that version of the plot, but yeah, this uses so oops. So we were sort of talking, you know, I was showing you plots that were going down here. They really run all the way down. Once the physics works for essentially massless particles as well.
Okay, so one more hand.
Awesome. Thank you for the nice talk. You mentioned this moderate tension with string theory.
Yeah.
If the data shows that this coupling constant is 3 or 4 orders of magnitude smaller, and you plow through all of those predictions, will string theorists say that that's it for string theory, or do they have sort of other backup stories?
I dare say, I strongly suspect string theory would survive this challenge.
Do you know sort of what box that puts them in, or where? Because you told the story that you look at the Yao manifolds and how you can wrap around the structures and you get these specific calculations.
Yeah.
What has to go away?
Yeah. I will share. I don't know enough string theory to really make a comment on that. But I know there are let-out clauses there on this. There are ways of compactifying that don't give you axions in the mass range that we would see.
Okay.
Sorry. So I mostly use this as motivation for why it's worth carrying on, because you know, if the cluster technique for looking at this, there is a pathway to detection here. I mean, the superradiance it's always a null experiment. You know, we can show they're not there, but we can't show they are there. But with the cluster work, you could imagine looking at getting a very high quality spectrum of an object of an AGN in a cluster, and finding those distortions that match axion models perfectly. So there is actually a pathway to detection there. So it's a motivation to dig down a little bit deeper, just in case there's something there.
That's an intriguing note to end on. So let's thank Chris again.